Welcome to the AI Research Roundup. I'm Alex. Today, we're looking at a paper from the Hugging Face trending list, published on September 27, 2025, which was about 11 days ago. The standout claim is a 1.7 billion parameter diffusion coder that matches or surpasses models up to 7 billion, while cutting latency by 39.6% versus Dream 7B Instruct. The paper is titled CoDA: Coding LM via Diffusion Adaptation. And as we'll see later, the results are really impressive. Beyond accuracy, the team shows confidence-guided sampling and a progressive masking curriculum that keep responses fast while enabling robust infilling and code edits. Also, the authors shared a full GitHub repo. You'll find the CoDA Hugging Face model class, TPU pre-training recipes, supervised diffusion fine-tuning with scripts, evaluation pipelines for human evil and MBPP, and a fast API serving stack with configurable generation knobs. There are quick start guides, checkpoint conversion utilities, and a bundled technical report. Alright, Figure 1 shows how the masking changes across stages, which matters because the model must learn from noisy text, but answer cleanly at test time. A progressive masking schedule means training gradually shifts the mask pattern to mimic inference. The top row depicts random masking during pre-training. The middle row adds unmaskable user and AS tokens to enforce prompt conditioning. The bottom row initializes a long masked block after a short prefix for infilling. So Figure 2 shows how the progressive masking schedule trains specific behaviors. Unmaskable means certain tokens stay fixed during corruption, so the model must condition on them. The S1 row keeps a prefix visible, which strengthens prompt following. The S2 row trims the tail and fills it with the pad token, improving robustness to short inputs. The S3 row uses contiguous mask token blocks, which directly teaches infilling and editing. Okay, while Figure 2 showed why the masking matters, Table 1 lists the pre-training corpus that teaches those skills. The mix spans web text, source code, mathematics, and academic writing, which promotes broad reasoning and robust infilling. The corpus totals about 179 billion tokens, where a token is a chunk of text like a word or symbol. The largest source is DCLM baseline, contributing about 60 billion tokens. A major code share comes from the Stack v2 Python, with about 51 billion tokens. Table 3 explains how often each masking strategy is applied during mid-training, which steadily ramps exposure so the model practices conditioning and infilling. S1 begins near 1%. S2 also starts around 1%. S3 starts at 5%. By epoch 5, S1 reaches 20%. S2 reaches 20%. S3 reaches 25%. So, Table 3 set the training mix. Figure 3 shows how compute scales during inference. Diffusion steps means the number of denoising iterations, so more steps raise time almost linearly. The solid blue curve rises slower than the dotted blue curve, reflecting about 40% lower latency for the smaller model. The red curves improve with more steps, but gains flatten around 512, which suggests capping steps without much accuracy loss. At small step counts, the compact model outperforms the larger one, likely because block masking lets it unmask several tokens per update. So, while Figure 3 covered scaling, Table 4 benchmarks accuracy across human evil and MBPP and uses pass at 1, which means the code works on the first try. CoDA 1.7b Instruct posts the strongest diffusion result on MBPP Plus at about 63%. The same model lifts human evil pass at 1 by roughly 25 points over its base, which underscores instruction tuning. Its eval plus average sits near 55%, and it beats similarly sized Gemma and LLM models. Alright, two takeaways stand out. A compact 1.7 billion parameter diffusion coder can rival 7 billion class models, and confidence-guided sampling, plus progressive masking delivers fast, reliable infilling with roughly 40% lower latency, and accuracy saturating near 512 steps. The broader implication is practical. Open diffusion coders for editing and completion workflows. Thanks for listening. I'm Alex, signing off.